zero matrix as the product of non-zero matrices. Hello, everyone. Let's begin our lesson by revisiting a concept you are already familiar with from your previous studies of real number algebra. You will recall a fundamental rule known as the zero product property. Essentially, this property states that if the product of two real numbers is zero, then it is a certainty that at least one of those numbers must be zero. To put this formally, for any two real numbers, a and b, if a times b equals 0, then either a equals 0 or b equals 0. This is a logical foundation we often use when solving basic algebraic equations. However, as we transition into the realm of matrix algebra, we discover a surprising twist. This property does not hold true. In matrix multiplication, it is entirely possible for the product of two non-zero matrices to result in a zero matrix. This means that unlike with simple numbers, you can multiply two matrices that both contain non-zero elements and still end up with a result where every single entry is zero. Over the next few slides, we will dive deeper into why this happens and walk through a practical example to see it in action. Understanding the concept. Now that we have established that the zero product property from real number algebra does not apply to matrices, let us dive deeper into the underlying concepts. First, let's define our terms to ensure we are on the same page. A zero matrix, which we denote with a capital letter O, is a matrix in which every single element is zero. On the other hand, a non-zero matrix is any matrix that contains at least one element that is not zero. It does not need to be entirely filled with numbers. As long as one entry is non-zero, the entire matrix is considered a non-zero matrix. As I mentioned in the previous slide, in matrix algebra, the condition that matrix A multiplied by matrix B equals the zero matrix does not necessarily imply that either matrix A or matrix B must be a zero matrix. You might find this surprising, but this occurs because matrix multiplication is not a simple element-by-element operation. Instead, it involves the dot product of the rows of the first matrix and the columns of the second. To put it simply, if the rows of the first matrix and the columns of the second matrix are orthogonal, which is a mathematical way of saying their dot product sums up to 0, the resulting element in the product matrix will be 0, even if the individual components used in that calculation were not 0. In the next few slides, we will use an analogy and a concrete example to visualize exactly how this process works. Conceptual analogy, the filter effect. Now, to help you visualize why this phenomenon occurs, let's use a conceptual analogy. Think of matrix multiplication not just as a calculation, but as a series of filters. Imagine that matrix A acts as the first filter. It takes a set of data and transforms it. It is possible that matrix A transforms this data in such a specific way that the output aligns perfectly with what we call the blind spot, or more formally, the null space of matrix B. Consequently, when matrix B processes this already transformed data, the result is completely wiped out. This leads to a zero matrix as the final product, even though neither filter, meaning neither matrix A nor matrix B, was empty or a zero matrix to begin with. To see exactly how this works with actual numbers, let's move on to a concrete, step-by-step example. Step-by-step example. Now that we have discussed the theory and the filter analogy, let us put these concepts into practice with a concrete example. To demonstrate that the product of two non-zero matrices can indeed result in a zero matrix, let us consider two specific matrices, which we will call matrix A and matrix B. As you will see, both of these are clearly non-zero. Our first step is to define these matrices so we have a clear starting point for our calculations. First, let us define matrix A as a 2x2 matrix where every element is 1. That is, the first row contains 1, 1, and the second row also contains 1, 1. Next, let us define matrix B. This is also a 2x2 matrix, but with a slight difference. The first row contains 1, 1, while the second row contains -1, -1. Before we move on to the actual multiplication in the following slides, please take a moment to observe both matrices. Notice that neither matrix A nor matrix B is a zero matrix, because they both contain elements that are not zero. This is a crucial observation, as it sets the stage for the surprising result we are about to find. Step-by-step example continued. Now that we have defined our two non-zero matrices, let us proceed to step 2, which is setting up the multiplication of matrix A and matrix B. To do this, we will calculate the product, which we will call matrix C. It is important to remember that in matrix algebra, the element in the ith row and jth column of the resulting matrix C is determined by taking the dot product of the ith row of matrix A and the jth column of matrix B. As you can see on the slide, we set up the operation as matrix C equals the 2x2 matrix containing all ones, multiplied by the 2x2 matrix, where the first row consists of 1, 1, and the second row consists of -1, -1. In the next slide, we will perform the actual calculations for each element to see if this product indeed results in a zero matrix. Step-by-step example continued. Now that we have set up our multiplication in the previous step, let us proceed to step 3, where we will calculate each individual element of the resulting matrix, which we are calling matrix C. First, let us find element C11. To do this, we take the dot product of the first row of matrix A and the first column of matrix B. This gives us 1 times 1 plus 1 times -1, which simplifies to 1 minus 1, resulting in 0. Next, for element C12, we multiply the first row of matrix A by the second column of matrix B again. We have 1 times 1 plus 1 times -1, which equals 0. Moving to the second row, for element C21, we take the second row of matrix A and the first column of matrix B. The calculation remains the same. 1 times 1 plus 1 times -1, which equals 0. Finally, for element C22, we multiply the second row of matrix A by the second column of matrix B once more. We get 1 times 1 plus 1 times -1, which equals 0. As you can see, every single element in our resulting matrix is 0. In the next slide, we will look at the final result and discuss the implications of this finding. Step-by-step example continued. Now that we have completed the individual calculations for each element, we move to step 4, the final result. If we assemble the values we just calculated into our resulting matrix, we can see that matrix C is a 2x2 matrix where every single element is 0. Therefore, matrix C is equal to the zero matrix, which we denote as O. This is the key takeaway from our example. Despite the fact that matrix A was not a zero matrix and matrix B was not a zero matrix, we have found that the product of A and B results in the zero matrix. This confirms that the zero product property from real number algebra does not apply here, a point that leads us directly into the common mistakes students often make when analyzing these types of products. Common mistakes. Now that we have seen a concrete example of how two non-zero matrices can produce a zero matrix, let's discuss some common pitfalls to avoid. First, be careful about applying scalar logic to matrices. The most frequent error students make is assuming that if the product of matrix A and matrix B equals the zero matrix, then either matrix A or matrix B must be the zero matrix. As we have just demonstrated, this is not the case. Always keep in mind that matrix algebra operates under a different set of rules than the real number algebra you are used to. Secondly, do not assume commutativity. It is a common mistake to believe that if A times B equals the zero matrix, then B times A must also equal the zero matrix. This is not always true. If we take the same matrices A and B from our previous step-by-step example and multiply them in reverse order, B times A, the result is a matrix with 2 and 2 in the first row and -2 and -2 in the second row. This result is clearly not the zero matrix, proving that the order of multiplication matters. Finally, ensure that you do not confuse the zero matrix, denoted by the letter O, with the identity matrix, denoted by the letter I to clarify. The zero matrix is one where every single element is zero, while the identity matrix is characterized by having ones along the main diagonal and zeros everywhere else. Keeping these distinctions in mind will help you avoid errors as we move toward our final summary. Key takeaways. First, we have explored the violation of the zero product property. As we discussed at the beginning of the session, in real number algebra, a product of zero requires at least one factor to be zero. However, in matrix algebra, this is not the case. It is entirely possible for the product of two non-zero matrices to result in a zero matrix. This brings us to the formal condition. If the product of matrix A and matrix B equals the zero matrix, this does not necessarily imply that matrix A is the zero matrix or that matrix B is the zero matrix. As for the reasoning behind this, recall our step-by-step example and the filter analogy. This phenomenon occurs because matrix multiplication relies on the dot product. When the rows of the first matrix and the columns of the second matrix are orthogonal, their products sum to zero, effectively wiping out the result even if the individual matrices contain non-zero elements. Finally, always keep in mind the principle of non-commutativity. As we saw in the common mistakes section, just because the product of matrix A times matrix B equals the zero matrix, it is not guaranteed that the product of matrix B times matrix A will also equal the zero matrix. In matrix algebra, the order of multiplication is critical. To wrap up our lesson, let us review the key takeaways to ensure you have a solid grasp of this concept.